Section 9.1, square root property and completing the square. Alright, so to start this section, we're going to first look at the square root property, which really gives us another way to approach solving quadratic equations with an x squared in them, rather than having to factor, which is the way we looked at in the past. So to demonstrate how the square root property works, let's first look at if we were asked to solve the equation x squared equals 36. Okay, so that's pretty much asking us what number, if we were to square it, would give us 36. Okay. And well, 6 squared gives you 36, so the solution would be that x equals 6. But also, if we took negative 6 and squared it, negative 6 times negative 6 would give you 36. So we actually get those two solutions, either 6 or negative 6. So in general, to define the square root property, if we have something squared equals a number or some value, well then there's two possible x values that could be solutions. Either the positive square root of whatever that k value is, or the negative square root of that k value. Okay? Just like the square root of 36 was 6, positive or negative. Okay? So recall the zero product property. This was the property we used when we were factoring to solve quadratic equations. So we'll look at that right now. To recall that property, it worked as if we wanted to get some product equaling 0. So in this case we have something like a times b equals 0. If that's true, then either one of the factors, the a, whatever that a factor was, had to equal 0, or the other factor, the b, had to be equal to 0. Okay? So in the past, when we had an equation like x squared minus 81 equals 0 and we're being asked to solve it, well, we would have to factor that expression on the left side of the equals, x squared minus 81, and then get that written as the product of two binomial parentheses. So we would factor this on the left-hand side, and x squared minus 81 is one of those special forms of a polynomial, is a difference of two squares. So that has a pretty specific way it would factor. Okay, difference of squares. X squared is clearly something squared, and 81 is a perfect square. So this would factor into x plus 9 and x minus 9 equals 0. So from that, we would get the two solutions. You'd look and see what x value would make this parenthesis equal, or what x value would make that parenthesis equal. So in the first parenthesis, negative 9 plus 9 would give you a 0 there. In the second parenthesis, if we took a positive 9, minus 9 would give you a 0 there. So that's like setting our a equal to c, what would make that equal 0, or what would make the second parenthesis, the b value, equal 0. So that's how we learned to do these problems up until now. Now we're going to look at this square root property and how that will work. So approach the same problem. So or use the square root property. Okay. So to use the square root property, let's start with the same problem. X squared minus 81 equals 0. Well, our first move will be to get the x squared term by itself. So we'd want to add 81 to both sides. Okay. This cancels out the 81s here. Gets us that x squared equals a positive 81. So now we can apply the square root property, which essentially what we're doing is we're square rooting both sides. Okay. If we do something on one side of the equation, we have to do the same on the other side of the equation. Okay? And as we learned in the previous sections, square rooting something squared cancels each other out. So that gets us x by itself. So then on the right hand side, square rooting square rooting 81 gets us 9. But remember, we get two possible answers, -9 or the +9. Okay? And going back to see if that checks, I mean, -9, if we square it, gives us 81, and then 81 minus 81 would give you 0. And then, of course, 9, if we square 9, gives us 81. 81 minus 81 gives us 0. So we have to remember with the square root property, it gives you the plus or the the positive or the negative value when you square root the right-hand side of the equation. Okay. So now let's look at a couple more trickier examples where we can apply the square root property. Slide this up. So next example, we have r squared equals 5. So this is already set up in a form we can use the square root property. Okay. We have something squared all by itself equaling something else. So we want to square root both sides of this equation. Okay. But remember, it actually gives us the positive or the negative square root. We can't really square root 5, so we actually have to write this as r squared, or not r squared, but rather r equals, and we can write this two ways. Saying positive or negative square root of 5, we can write plus or minus 5 like this, which is another way of saying that r equals negative square root of 5 or positive square root of 5. So on a test, this notation I would be fine when accepting of this. Although when you do your My Math Lab homeworks, you're going to have to write negative square root of 5, comma, positive square root of 5 to list the two examples, or the two answers. Okay. Alright, looking then at the next examples, not exactly in a setup form yet that we can use the square root property. We have to get it down to something being just, something squared equaling everything else on the right hand side. So our first move would be to get that 48, that minus 48 to the other side. So we would want to add 48 to cancel it out here, and add 48 on the right hand side. Okay. So those cancel. So we're left with 4x squared equals 48. We're still not in a correct form yet because we have a coefficient in front of our x squared term. So we have to divide by that coefficient 4 to get just our x squared all by itself, because those 4's will divide each other out. Okay. So taking this up over here, we are left with that x squared equals 48 divided by 4 gives us 12. So now we can apply the square root property. Okay. If we square root the left side of the equation, the x squared, that's going to be equivalent if we get, I guess it's going to give us the positive or the negative square root of the right side of that equation, 12. Okay. So here the square root and the square cancel out. We're left with x. So it either equals negative square root of 12 or positive square root of 12, because we can't actually square root 12. However, in this example, this is different than when we had the square root of 5, because we can simplify this root. Even though we can't square root 12, 12 has a factor that we can square root, that factor being 4. So we can rewrite this as x equal to positive or negative, because we have the positive or negative. We can break down 12 as the square root of 4 times the square root of 3. Okay. So x is going to be equivalent to either the positive or negative. Square root of 4 gives us 2, so 2 square roots of 3. So either negative 2 square roots of 3 or positive 2 square roots of 3 would be our two solutions. So again, you can write it like this, or you could split it up as two separates like that. But you do have to simplify. You can't just keep it as a square root of 12. Okay. Looking at our next two examples, those look completely different. We actually have parentheses involved, but they're actually set up in a form that's nice, a form we like. This is still saying something squared equals something else. So that actually already in a form we can use the square root property and right off the bat. So let's try doing that here. We have x minus 5 squared equals 49. Okay, well, if we want to cancel out that square, that power of 2, we would square root that left side. And it would leave us with just the x minus 5. But using that square root property, that gives us the plus, the positive, or the negative square root of 49 on the right-hand side. So again, the square root and the squaring cancel each other out, and we're left with just x minus 5 equals square root of 49 is 7, so either the positive or negative 7. We don't need the square root anymore since 49 was a perfect square. Okay. So I guess how we can handle this then is we can really drop those parentheses. We don't need those anymore. We want to get x by itself. So what we want to do is add 5 to both sides. Add 5. Okay. That cancels out the 5's over here. Leaves us with x equals, so what we have is 5 plus or minus the 7. So if that notation is confusing you, you can go ahead and split that up into two different expressions. So either x equals 5 plus 7 or 5 minus 7. Okay, that's all that plus or minus notation means. So 5 plus 7 would give you 12, or 5 minus 7 gives us negative 2. Okay. We can always go back to make sure these answers are correct by checking them. Okay, if we take the 12, plug it back into this original equation, 12 minus 5 is 7, and then 7 squared gives you 49. Or negative 2. Negative 2 minus 5 gives you negative 7. Negative 7 squared gives you 49. Okay, so there's our answer. I just thought about it in this section. It might have you even write the answers in that set notation form. So you would just write negative 2 comma 2. Okay. Can't remember for sure, but I believe in my math lab and some it might have you write it in that form. Okay. So last example here looks kind of like the example we just did. And it's going to work very similar then. We have something squared equaling something else, so we can go ahead and square root both sides. Okay. It's already in a form we can do that. So if we square root this left-hand side of the equation, we'll cancel out that power of 2, and then we're going to get the positive or negative square root of 18. Okay. So square root and square cancel each other out. And we're left with 2x minus 3 equals either the positive or the negative square root of 18. So what we would have to do here, we are going to have to break down that square root of 18 because it has a factor that can be square rooted, that being a 9. Okay, 9 times 2 gives you 18, and 9 we could square root. So we could do that now, or we could wait here. Why don't we wait to do that till the end? So our whole goal is to get x by itself, so we need to get rid of this minus 3 first. Let's add 3 to both sides. Okay. When we do that, we get 2x equals 3 plus or minus the square root of 18. then we need to divide everything by 2. Okay. Just to save space, I'm just going to write it here. X equals, if we divide by 2, we'll cancel out the 2 there. And we're going to have 3 plus or minus the square root of 18 all over 2. So that'd be like saying x equals 3 plus the square root of 18 over 2, or x equals 3 minus the square root of 18 over 2. However, you would be expected to break down that square root of 18. So let's do that now. The square root of 18 equals the square root of 9 times the square root of 2, and the square root of 9 is 3, so it's going to equal 3 times the square root of 2. Okay. So for our 2 possible solutions, kind of running out of space here, let me slide another sheet in. So for our 2 possible solutions, we have that x equals, okay, 3 minus 3 square roots of 2 all over 2, or 3 plus 3 square roots of 2 all over 2. Okay? So we're kind of just taking what we had here and replacing square root of 18 with 3 square roots of 2. Okay? And we can't simplify these 2 fractions because 2 doesn't divide this 3 or this 3. The only way you can reduce is if you could reduce the 2 with this number and that number in front of the radical. So that's as reduced as we can get, and there are your 2 answers. Okay. So that's it on that side. Let's go to the next page of the notes. And we have a section on what's called completing the square, which is actually a concept not completely covered in Math 0306 anymore. So we're not going to completely cover it as in depth as the notes originally would, but I will give you enough to answer the questions you will be tested over or will be tested over when we take the final exam. So completing the square is a method where we write a quadratic, okay, something in the form ax squared plus bx plus c. We get it into a form so that it can be factored into some binomial squared. Okay, so this when you factor it, it equals the same parenthesis times the identical same parenthesis. So let's notice some things about these perfect square trinomials that we have. Okay, x squared plus 10x plus 25. You might not notice it right off the bat, or with any of these 3 polynomials, any of these 3 trinomials, but they're all perfect square trinomials. Because watch what happens when we try to factor them. Okay, if you remember your rule, we're looking for 2 numbers that multiply to give us 25, add to give us 10. Okay, well, in that case, the numbers would be 5 and 5. Because 5 times 5 multiplies to give us 25 and adds to give us 10. Okay, but when we factor something and it's the identical 2 same parentheses, we could write that as x plus 5 squared. Okay. And that makes it look like something we were dealing with on our problem, on the last 2 problems we just handled. That's kind of how this relates. If you have something squared, we could always square root it to cancel out the square and end up solving an equation for x. Let's kind of get ahead of ourselves though. Let's look at the next one. 2 numbers that multiply to give us 36, add to give us 12. Okay, well, that would be 6 and 6. 6 multiplies with 6 to get 36, and 6 plus 6 gives you 12. But again, because you can write it as the same binomial times itself, we could write it as that binomial squared. Okay. And then lastly, we have a little bit different here because we have a sign, but 2 numbers that multiply to give us 9 and add to give us negative 6. Well, those numbers are going to be a negative 3 and another negative 3. 2 negatives multiply give you a positive 9. Negative 3 plus negative 3 gives you negative 6. So after you're factoring, you see it is a perfect square trinomial because it factors into some binomial squared. Okay? But some things that I wanted you to get to notice when we do this. Okay? In every perfect square trinomial, which that's what these three things are, if they factor into a form like this, then it's considered a perfect square trinomial. But in order, our C value, okay, the number that was the constant value that was written on the end of each trinomial, that number could be found by taking the B value, the number in the middle, and halving it, dividing it by 2. 10 divided by 2 gives you 5, and then if you square that number 5, it gives you 25. Halving 12 gives us 6, and then squaring that would give you 36. Halving -6 would give us -3. -3 squared gives you 9. So the idea is that the C value, the number on the end here, it could be found in every perfect square trinomial by taking our B value, dividing it by 2, and then squaring it. Or we could think of it as the C value is going to equal our B value divided by 2 squared. Okay. So, in these problems, I cut out all the problems that ask you to actually complete the square. But in the homework, you will see some problems that ask you what number would you have to, what C value would you have to include in order to complete the square, in order to give yourself a perfect square trinomial is really what that's asking. So we'll just look at this first example. Okay, that's asking you to complete the square. So the idea here is this right now, if we tried to factor, is not going to give us a perfect square trinomial. Matter of fact, there are no numbers that can multiply to give you 10 that will add to give you 8. So this isn't even in a nice factorable form anyways. So what we want to do is, since it's not a perfect square, we want to move the constant term. Okay, so minus 10 from that side to get rid of it, so we'd have to minus 10 there. Okay, so it's not a perfect square. Move the constant to the other side. So then that gives us here, x squared plus 8x equals -10. Really, we don't need to worry about this -10 anymore, at least for what I'm going to be testing you over. So really what we're just trying to find is what value needs to go here. Okay, so what C value is needed to make a perfect square? And here's where we can use that formula we just kind of created up here. The C value is going to equal the B value divided by 2 squared, which in our case, our B value is 8. So 8 divided by 2 squared, well, that's just going to be 4 squared, which is 16. Okay. So in the problems you have to answer, all you're going to have to say is this, that C value is 16, and that would make the perfect square. But I guess I can show you how it would have worked if you were going to actually have to complete fully complete the square. So what we would do then is x squared plus 8x. We'd be adding in then that plus 16. Okay. Well, the original equation was equals -10, but since we're adding in a 16 here, we'd have to add a 16 on the other side as well. And then what we have here is a perfect square trinomial. So this would actually factor into x plus 4 squared, because we'd be looking for two numbers that multiply to give us 16 and add to give us 8. That'd be 4 and 4. So you'd have 2x plus 4s, 2x plus 4s, just like all of these factored up here. equals, on the right hand side, negative 10 plus 6 would give us positive 6. Okay. So how we could then finish the problem, well, now it's in a form like we handled on the first page of these notes. Square root both sides using the square root property, and so this would tell us to get rid of that square root, or that square, we would square root this side, and we get plus or minus the square root of the right hand side, 6. So we'd get x plus 4 equals plus or minus square root of 6, which would give us a final answer of x equals, we'd have to subtract 4 from both sides. So a negative 4 plus or minus the square root of 6. Okay. So what we did right there is we completed the square to solve in order to solve the equation. But again, really all you're going to have to know how to do is find that value, that 16, that makes this expression a perfect square. Okay? So I'm going to skip the next example. Just go down to our last example here. And it's actually more along the lines of what we were doing on the front page of the notes, using the square root property, but what happens to get when you get a non-real or a complex solution, okay, involving imaginary numbers. So let's look at that. We have t plus 2 squared equals negative 16. So we could use the square root property on this. So if we were to square root this left side and square root this right hand side, we'd get the plus or minus on the right hand side. So here the square root and the square cancel out. We're left with t plus 2 equals plus or minus. Well, the square root of 16 is 4, but we have negative 16, square root of that. So remember that it gives us a 4i, because the negative one part of it when we square root becomes an I. So then, to solve this, well, we would subtract 2 from both sides. So our answer would be, well, I guess I could just write it right here, t equals negative 2 plus or minus 4i. Okay. Or once again, that would be like saying t equals negative 2 minus 4i, or negative 2 plus 4i. Okay. Either those are your two possible solutions. So just like we did on the front page, just if you're dealing with a negative that you end up square rooting, you're going to end up getting an imaginary solution, so something with an I in it. Alright, and that concludes everything from section 9.1.